let's do a Calculus 2 problem, just to kind of remind you of what you did back then. Now, it won't quite look like a Calculus 2 problem until I convert it to parametric equations. So in part A, it says sketch the graph given by, okay, R of t, this is called, just in case I haven't made it clear, R of t is called a vector valued function. The input is a real number, t, so there's the input, t. The output is a vector. Does that make sense? The output is a vector, so it's called a vector valued function because the output is a vector. Now, to convert it to something you learned about in Calc 2, all you have to do is realize that, I need to erase this part. All you have to do is realize that you could set x equal to 1 minus t, and you could set y equal to the square root of t, and you've got your parametric equations. So I'll write them over here. In parametric equation form, all we're saying is x is equal to 1 minus t, and y is equal to the square root of t. So these are your parametric equations associated with the vector valued function. And that's how it was presented to you in Calc 2 as parametric equations. Now, be flexible. Be able to write it in the vector R of t format. We would use the usual terminology. The parentheses t, R parentheses t, means R of t, just like f of x. F parentheses x means f of x. But the output's a vector instead of a number like you're used to. Okay, so be able to write it in vector form or parametric equation form. So if you think back to Calculus 2, to graph something like this, maybe you just made a table, right? T, a column for t values, a column for x, and a column for y values. And again, in case I haven't made it clear, if you just take all the ordered pairs with first coordinate 1 minus t, x, second coordinate square root of t, y, all of these ordered pairs define your curve. So that's why it makes sense, if you want to get an idea of what this curve looks like, is to plot a t value. So you pick a t value, t is your input, and then see what your output is in x in terms of t and y in terms of t. Okay, so what kind of t values do you want to plug in? Are we allowed to plug in negative t values? It wouldn't hurt x, but what about y? Y is the square root of t, so we're not going to look at complex vector valued functions here. That's a whole nother class. So, so the domain, the allowable domain would be t values greater than or equal to 0. The inputs are t values greater than or equal to 0. So that's a good note to make. The domain would be t is greater than or equal to 0. So it's the smallest domain of the two parametric equations. So the domain is the set of all inputs. You're allowed to plug in the set of all t values in this case because t represents the input. And you can plug in anything you want for x, but you can't plug in anything you want for t, for y that is. You can only plug in t values bigger than or equal to 0. So that's the domain. It's the smaller, it's the overlap of the two domains for x and for y. So in interval notation, you would say from 0 to infinity. That's what you're allowed to plug in. And then it would be handy to plug in values that are perfect squares because you're going to end up taking the square root to get y. So how about 0, 1, 4, and 9 maybe? So going down the x column, what do you get? So you're just think of plugging in either the parametric equation or just right here, what do you get for your x values? Given these t values, what are the corresponding x values? Plug in 0, you get. Plug in 1, you get 0. Plug in 4, you get -3. Plug in 9, you get -8. So it really is just plotting the x values. Okay, plot the y values corresponding to these t values, right? So, okay, so just plug in there. What's the square root of 0? Square root of 1 is 1. Square root of 4 is 2. And then square root of 9 is 3. So then when you graph the thing, you're focusing on these ordered pairs. You're going to connect the dots after that. So here we go. Let's see. I don't know if I want to plug in the one with 9 as your t value, but I'll plug in the 0, 1, 4. So it looks like it's going negative, so maybe I can fit in the negative 8, 3. And then I need to go over here. And the highest it gets, it looks like, is 3. So I just need to go up 3 hash marks here. You don't have to go by ones, by the way, but I think that's the most convenient value to go by here. So plotting the points. 1, 0 right here. 0, 1 here. Negative 3, 2. Right here. And then negative 8, 3. So if I counted right, it'd be right about there. I didn't go up high enough, I don't think. So I'm going to connect the dots in a nice smooth curve. What happens if I don't quite make it through my point? Am I going to start all over? No, I'm going to make the point bigger. Okay, so, it's kind of hard to draw a nice smooth curve, but it really should look like half of a parabola. So I'll try to fill this in a little darker to make it look a little not as weird and oscillating as it looked. Okay, there, that looks better. Now, you can also get an orientation, because if you think of the parameter t as time, then you could think of this as a path that a particle takes at a certain time t. The position of a particle, r of t, could represent the position of a particle at time t. And since t starts at 0, when t starts at 0, you're at 1, 0, and then it goes at time 1 second, 1 minute, I don't know. It goes to 0, 1, and then at time 4, it's at negative 3, 2. You can see that the path that's traveled here has this sort of, I guess it's a kind of almost counterclockwise orientation, isn't it? So that's something you get with parametric curves that you don't get with Cartesian coordinates, right? Okay? With Cartesian functions, I should say. Does that make sense to you? So the purple arrows indicate the way a particle would travel with respect to time along that curve. Any questions there? Do you remember how to eliminate the parameter? If you look again at the parametric equations, let's say you wanted to eliminate the parameter. Okay, so that's basically the answer right there. But let me give you more for your tuition dollar here. If you have x equals 1 minus t and y equals square root of t as your parametric equations, do you remember how to eliminate the parameter? What do you do?
Don't you plug one into the other one?
Yeah, but you have to do something first. You want to get it as a single Cartesian equation, x and y, no t.
Once you square t, you get y squared equals t, and then x equals 1 minus y squared?
Yeah, so that wasn't what I thought. I thought, it would work. It would definitely work. I was thinking of solving this one for t in terms of x, but your way would work. So let's do it your way. So if you square both sides, he's saying you get y squared is equal to t, right? And then, if y squared equals t, then I could go ahead and just plug it right in here. So this is another version of solving a system of equations, right? Except we don't get numerical answers like you're used to. We've just eliminated the parameter, essentially. We've eliminated one of the variables. We had 3, now we're going to have one equation. We had 2 equations with 3 variables, now we're going to have one equation with 2. So we eliminated one of the variables. So what do we get? We get x is equal to 1 minus y squared. Now you have to realize, though, that there are some limitations, right? If you graph the curve x equals 1 minus y squared, you would get the other half of the parabola, right? You would get, let me do it in a different color. You would get this half of the parabola. It'd be the mirror image of the half in red across the x-axis, wouldn't you? But that's not, you cannot say that that's part of our graph. Because what we're doing is graphing just half of it. So how could you, so this equation doesn't quite work, I guess is what I'm trying to say. Because that equation represents the full-on parabola opening sideways, right? So if you solved it for y and took the positive square root, because y, you can see y is positive, I think you'd have the picture of the graph in red without the orientation anyway. So let's see, y squared would equal 1 minus x. Would you believe that from this equation? Add the y squared, subtract the x. Take the positive square root, and that would be the equation. So that's the way you eliminate the parameter. So you take one of the equations. You could have taken the top equation and solved for t as well. And then you would have gone right to this, by the way. But the idea is to solve for t in one of the equations and then substitute in the other equation. It's like the substitution method from solving systems of equations. And then the idea is then you'll have just one equation with x and y, and you've eliminated the parameter t.